Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Rich Sherville visiting us from Sandia Labs. Rich is an early inventor of a factoring method and the hasty pudding cipher, and also a co-inventor of elliptic curve point halving. So today he's going to speak to us about the SANDstorm hash function. Thank you.
Okay, can you hear me? All right. This is actually a three-part talk. The first part's the hash function, the second part's about elliptic curves, and the third part is about fun stuff. So I'll be a little zippy, but I hope I can at least keep you interested. Let's see. Does everyone know what a hash function is? Okay, we can skip the first slide. We can skip the second slide. Okay, we're sort of getting to where we need to be now. There are these hash functions. MD5 has been around forever. I guess everybody here was probably born before MD5 was invented. That would have been in school. Anyway, MD5 is broken. SHA-1, this slide is actually several months old, and in the meantime, SHA-1 has gotten closer to being actual broken. The main reason for worrying about SHA-2 is it's the same design on steroids. What's happened is MD5 got beefed up and became SHA-1, and that got beefed up further and became SHA-2. And so there's some question about, is this a good way to design a hash function? You know, it seems to produce random-looking numbers, and then about 10 years later, somebody comes along and finds a way to wiggle in and break the thing. So NIST has set up a contest to produce an alternative or a backup for SHA-2. Okay, we had 64 submissions by Halloween. They took 51 first-round candidates, and the requirements were basically that you look startled.
I was wondering about the drop from 64 to 51.
Oh, well, okay. The spec had to be at least readable, and it had to compile and run in the NIST harness and produce some sort of answer. And that got them down to 51. We have about 22 unblemished survivors at this point. There's a lot of argument about what's a blemish. So the 22 is a very fuzzy number. NIST has said at crypto, maybe after crypto, they'll cut down to 15 submissions. These are the list. And this may be out of date since the slide's a month old. And you can see there's quite a bit of innovation in the names. And a number of good ideas have shown up in the hash functions. And the best attack column sort of indicates the situation with attacking the hash function. Green means that it's an attack against some much weaker version of the hash function. So the fact that they found something doesn't actually mean much one way or the other. Let's see. Backspace. Red is dead, where there's actually been a collision produced. Orange is some slightly defective collision in some sense. Like maybe they weren't starting from the right IV, or it's a theory collision, you know, with...
Just any attack which hasn't been implemented.
Ah, okay, all right. So a theory collision. Okay, SANDstorm is required to have 4 different length outputs. And they're not supposed to be truncations of each other or something simple like that. They actually have to be different. It basically has to plug and play with the SHA-2 spec in terms of same inputs and outputs and so on. So it could be a drop-in replacement. We used a truncated tree for reasons that will be clear later. The tree is sort of based on Merkle-Damgard chaining. Most of the hash functions use the same ideas. They don't use the tree, though. We have very simple padding. We stick a 1 bit on the end of your message. The length goes in later to make sure that you can't mess around with it. And we have a finishing step to make sure that, well, you can't mess around with it. Okay, we use what's called a very wide pipe. The internal state of the hashing is much wider than the final output. That makes it harder to get internal collisions in the hash. It also gives us resistance to all the various attacks that people have invented. We have what we regard as a very serious commitment to parallelism. Most of the submissions, instead of having a parallel mode or anything, they just have a little sentence saying you can use a tree mode if you want. But that means you'll get a different hash value if you use tree mode, which means if you and I are both hashing the same thing, we both have to match on the mode we use. So we have to have made some sort of agreement that we were going to use tree mode, and perhaps we're going to use tree mode with particular parameters and so on. SANDstorm is a limited size tree, period. We don't have to agree on these mode parameters or anything. So in a sense, it's a much more limited fixed design. Most of the designs have implicit parameters. Or, they haven't done anything about tree mode other than add a sentence at the end of their write-up. We're set up for parallel. We can be parallel in several different ways, at the hardware level and various software levels. Everything from gates up to you can farm the hashing out to 100 different processors and bring the results back and bring them together and get the same hash answer. One of the things we put in is if you have a big message that's the same most of the time, like a movie, and you want to put a wrapper around it identifying who got this copy, then you're not going to have to rehash your movie each time with our hash function. You can arrange your wrapper so that everybody you send it to will get a different thing that'll have a different hash value, but you don't have to take the time to rehash the movie. One of the points of the finishing step is to make sure you can't just stick extra message on the end. That's a known weakness of a lot of things.
So that wasn't part of the challenge, those features?
Well, the NIST, they had a list of requirements at the beginning, and they said, we would really like it if it were not susceptible to the following list of attacks. And they included basically all known attacks on serious hash functions. And that includes length extension as one of the things you're not supposed to do. This is our mode. We have a compression function that operates on blocks. And the first block goes in this box here. And it produces this red arrow, which is, I guess it's 4 hash function lengths. It's the output after rounds 1, 2, 3, and 4. And that is input to every other hash operation. So if you're dividing the work over multiple computers, you have to send out a copy of that to the other computers to work with. Beyond that, we take the message in units of 10 blocks. Yes?
You have a decimal tree structure?
Yes.
Okay.
Yes. There's not time. I could go into the choice of parameters. It doesn't hurt anything at all, and it turns out to be a good choice. Within this block, the next 10 blocks are fed through, in effect, a Merkle-Damgard chaining, although it's a very wide pipe sort of arrangement. And the result of that goes into level 2. And similarly, it's processed 10 blocks at a time, and these can all be on different computers if you've got that many computers. Then the level 2 is doing the same deal, only it's 100 blocks at a time. Then if you actually have a huge message, you get into level 3, and the results from the level 2 just get passed in there. The final output goes into the finishing step, and then there's the answer here at the bottom. Now, you don't have to use any of this if you don't have, if your message isn't big enough to need it. So if you have just a one-block message, you'll get this box, and it'll be fed down immediately into the finishing step. So you run compress twice. If you have a 10-block message, an 11-block message, or up to 11 blocks, you'll get this, you'll get this. These two get dropped out, and it'll feed into the finishing step, and so on. So the result is, if you have a small message, for various kinds of small, you don't use this extra overhead here. And you don't need the extra storage associated with it, and so on. Okay, a summary. There are initial and final compression runs. You have between 0 and 3 intermediate levels, depending on what you need. Early out means if you don't need an intermediate level, you don't use it. This gives a possibility of a factor of about 1,000 speed up. You could assign all this to different machines and get up to 1,000 speed up if you had 1,000 computers to do the work on. Of course, there's always communications overhead and stuff. So you'd need to be hashing a movie or something for it to even be worthwhile. But the first block appears in all subsequent compressions, one way or another. So you can't lose the information in the first block by just putting in a huge message. Between the individual blocks within a box, you have 4 times the output as the size of your pipe. When you're passed down to the next level, you only have double size, which corresponds to the size of one input block. And I need to move a little faster here. This is what inside the compression function. There are 5 rounds numbered 0 to 4. Basically, the block is passed down. So the initial block for SANDstorm 256 is going to use 512-bit blocks. The block input, the message input comes in through the M's. The internal state is half a block size. So you have 256 bits passed along these down arrows. You pass 4 of them to the next compression function. So this is in total 1024 bits. The data from the message comes in as more 256-bit values. These are all XORs, wherever the arrows meet. And it gets passed down and processed. The arrows are arranged so that this is compatible with hardware pipelining. You could have a pipeline that was operating, part of the pipeline would be working on round 4 of this message block. The next part would be working on round 3, the next one on round 2, and so on. So each round could be in a separate pipeline stage if you wanted. We reuse the SHA-2 constants on the assumption that SHA-2 is always going to be around, and this is, quote, a backup system. So by reusing the constants, we avoid needing some extra memory. This is one little step of that previous slide, gives you a close-up on how the arrows are arranged. In particular, it's important that this arrow happen after this one arrives so that the pipelining can operate properly. Let's see. The arithmetic, the main thing about the arithmetic is it uses a multiply instruction. The rest of it is pretty much standard stuff. Multiply is wonderful for 2 reasons. It's a superb mixing operator, and it just kicks the hell out of differentials. In addition, if you are so inclined, you can actually design a fast parallel multiplier. It's another place you can put in parallelism if you really want to throw gates at it. We have a minor use of the AES-S box, and we interleave arithmetic and logic operations. Yes?
Your multipliers are very, very big, like 64 by 64. How do the 8051 guys react to that idea?
The which?
The guys with the tiny 8-bit processors.
They can live with it because our total number of rounds isn't very high. Let's see, we also put in a tunable security parameter because the NIST requirements, they didn't say you had to have one, but they thought it was a good idea. And what we do is we just rerun round 4 more times if needed. My guess is in practice it will never be used, but it's there and tested and so on. One other thing to mention. Defense in depth. Our feeling is that all the hash functions that we've seen that have been used a lot have turned out not to be strong enough. And the appropriate thing to do is to have more stuff in at the beginning, even though it's going to slow you down. In most cases, the thing that's slowing down your application is not the hashing. It's something, there'll be something else that's your real slow step. It's very unusual for the hashing to be the slow step. So we can afford to put more work into the hashing. The point of that is to avoid having to replace it 10 years from now. I guess SHA-1 has lasted, 17 years now? People are still using it. It's going to be a while before it's phased out. And it hasn't technically been broken yet. So. Okay, the internal arithmetic. For the 64-bit, the 512-bit hash, which produces a 256-bit output, takes block size 512, mostly operates on 64-bit words. And the internal multiplication stuff is 32 bits in and 64 bits out. So we break up a 64-bit word into 2 halves. We have an F function that just adds the squares of the 2 halves. And mod 2 to the 64th means it's just barely possible that this could overflow. And the G function does that. It also takes the 2 halves, adds some constants, does the multiply, and then does the swap of the 2 halves. That's what the rotate 32 is. And again, it's all mod 64. We have a choose function. S box of Z takes the low order byte only of a 64-bit word and replaces it with the S box value on that byte. And people used to complain, well, that's a table reference, but of course Intel is about to give us an S box lookup instruction with constant time. So that's less of a problem. Then we also have an operation we call bit mix that takes 4 64-bit words and just in each column rotates by none or 1 or 2 or 3 places. So you have 4 words in and 4 words out, but the bits have been picked from each of the 4 words to make one word. This is bit mix, nothing to say about it. The round function, there are 4 64-bit words, and we apply this function to each of the words, and it basically does a bunch of arithmetic. We then follow it with a bit mix to guarantee that everything influences everything. Each byte of output is a function of every bit of input. Roughly 40% of the work of a compression is in the round function. The 60% is in the message schedule. That's a little bit unusual to put so much work in the message schedule. But if you look at all the breaks, the place where they get in is the message schedule because the message schedule is too easy. And when the message schedule's been harder, that's been a better defense. This is our message schedule. It's sampled 5 times from the message. The initial message, we simply do a bunch of mixing up the bits to make sure every bit gets into the 0 round run of the function, the mixing function. Then we have this iteration where we take stuff from the previous 8 words and apply a magic function to it, and that becomes the new word in the message schedule. And then the actual length is 32, 33 steps. We pick sub-blocks of 4 out of that. So we'll take 4 at a time and feed it into the round function. But we don't just take 4, 4, 4, 4. There's 4, and then there's a gap of 1, 4 more, gap of 1. And then there's a big gap at the beginning between the round 0 setup and the round 1 inputs. And we've done some checking to make sure that all the bits here influence all the downline bits after a couple of steps and so on. About 60% of the work of hashing is in the message schedule, which incidentally, should you be inclined, can be parallelized in a separate thing. And actually, when we recoded this for the X86 64 architecture, I took advantage of that. And I moved the message schedule into one set of registers. And that's fed to one of the core, sub-core processors. And I had the round function in a different set of registers and so on. And it all runs fast. This is a summary of the god-awful 64-bit X86 architecture. I'll get to the next slide so nobody chokes. This is our current performance situation. The original submission was in nice portable ANSI C and was god-awful slow. This has been improved quite a bit. Single core assembly language is about 15 clocks per byte. The compression function runs at 13, and we have 10% tree overhead. On long messages, you'll pay 10% extra compressions than just taking the message blank would be. In C, dual core is 10 clocks a byte. I think on the Linux I can actually get it down to 7.5, but I don't have the dual core code running yet. This is on the NIST test machine. Well, of course, Linux isn't part of that configuration, but it's equivalent. And someday I hope to have it even under Windows Vista dual core, but that's not right at the top of my list right now. 512-bit C, we have something that's sort of like assembly language called Intrinsics, which is basically C language calls to the assembly code, to the assembly instructions. On a single core, that's 24 clocks a byte. Then we have a machine down in the lab, which is a dual quad core. That's got 8 processors in it, tightly connected, and that does 2.1 clocks per byte, which is 6 or 7. It's basically linear speed up with some overhead. We have something called the Sun Niagara. I'd never heard of them, but apparently the gadget has 16 threads and gets a linear speed up. You can get more threads even though there are no more processors. So you have the processor, the thing that actually does the arithmetic, and then it connects to one or another set of registers for each individual thread. So the processors can have up to 8 threads per, and the speed up on doubling the number of threads there is basically times 1.5 each time, which is about what you expect for a parallel processor that doesn't really have that many processors in the bottom. The point of all this is actually the same sort of thing you'd expect for a typical talk about parallel programming. Yeah?
Rich, am I reading that right? You're going from 2 cores to 8 cores. You seem to have gotten more than a factor of 4 speed up.
It's dual quad core.
This is a
dual quad core.
Dual quad core. There are 8 processors there.
And the dual core has 2.
Right. This is in C, though. This is the assembly code.
Got it.
Sorry. I threw this together this morning based on some other notes. Okay, scratch memory. This is here because of Niels. Niels produced this list of these functions are good, these are not so good, these are just barely good, these are awful. And we came in at the bottom of just barely good. And one of his criticisms was we were using too much memory. So I actually sat down and worked out how much memory was required. For SANDstorm 256, a 1-block message, it's actually 1 block with padding. So you have 511 bits of message plus a padding bit. You will need 128 bytes of scratch space. And that will give you, as part of that, you'll have a hash value in 32 of those bytes at the end. And I'm assuming, this includes the message being copied into the first 64 bytes, and, I'm free to stomp on it and so on. Now, if we go up to a larger message, a message of 3 blocks needs 200 scratch bytes. A message of 11 blocks needs a little bit more. 1,000 blocks needs a little bit more. You go over 1,000 blocks, you'll need a little bit more. So what we're coming down to here is that you can hash small stuff in a couple of 100 bytes of scratch. For SANDstorm 512 and 384, everything is doubled. It's the same number of blocks because the blocks are double size. The scratch space in bytes is doubled. In particular, if you're doing any kind of public key operation, these numbers are less than you'll be using in your public key operation anyway. so you can share the scratch memory. Okay, feature summary. 64-bit design, and for the long hash we've used 128 bits. Block size 512, that's standard. A brick construction, by which we mean that if you take one of the parts and kick it and take it out of the thing, you still expect to have a secure hash function. Now that was a design goal, and we mostly satisfy that. But I can't say for sure that we got every part covered. Multiplication is the best mixer. It's annoying that you cannot write C code that efficiently uses multiply. You have to throw away the bottom half or the top half or something, which means that a portable implementation is going to suffer in performance. It means there will always be assembly language sitting there at the bottom doing that multiply for you if you need the performance. Let's see, what do we do here? Oh, one other design decision. Most of the hash functions bring in the message a little bit at a time, like one word at a time is very typical. This, we think, has turned out to be a design weakness in practice. It means that somebody who's sitting there trying to mess with you gets to play with the individual parts of the message schedule and tweak here and tweak here and tweak here and verify how the bits manipulate and fall down. If instead you bring in enough message to cover the whole state at a time, he can get you on one round, but then he's stuck on the round either before or after. That's the deal here. 60% of the work, I mentioned this, serious parallelism. There's no separate mode for SANDstorm. It has a maximum possible speed up of 1100 or something in terms of divvying it up among multiple computers. Well, actually even more if you did. You could do the message schedule separately. Anyway, but that's it. You know, we're not going to have a tree that could be infinitely tall and you have to allocate extra memory for or something. We just fixed it. And the parallel mode gets the same answer, the same hash as somebody who's sitting there doing it serially. So we have a standard. That's the point. We have the tunable security parameter because it's kind of required. Wide pipe design. Block numbers get put in everywhere, which prevents people from various length stuff, and for moving the blocks around, which you don't want to happen. Parallelism. I guess I've said all of these things individually before. If you want to do movies where you don't recompute the hash, then you have to arrange your format so that the first block is fixed, because the first block is put into everything else. So your movie is going to have to start out with copyright, Panavision or something. That'll be block 1 of the message. Block 2 through whatever is part of your wrapper. You can put more wrapper in wherever. You probably want wrapper at the end, but maybe in the middle and various places. If you fix the first block, then all the other parts of the hash can be pre-computed where you have fixed stuff. So this is where you're hashing something and you only want to recompute your changes in essence. This is the pitch for multiply. Far and away the best mixer. If you have an XOR operation, every bit in your result depends linearly on 2 bits of the input. My definition of depends is that if you flip a bit, it's got a 20% or higher chance of changing the answer. For add, it's a little bit more. Each bit depends linearly on 2 bits in the same position and non-linearly on the next 2 bits over, and a little bit on the bits beyond that. So the realistic answer here is 2 linear, 2 nonlinear. Multiply, every bit on average depends non-linearly on 32 bits of the input. The cost of a typical multiply is actually only about 3 clocks. If you look at what the computer's doing, you know, you've got this 500 million bits of gates on the chip. All of that work is going to make happen a few arithmetic operations at each turn, at each cycle. You know, the part that's doing the arithmetic is maybe a couple thousand gates. Everything else is devoted to getting the operands down to this little part that's doing the arithmetic. So it makes sense in terms of balancing your overheads to get as much work as you can out of that arithmetic. Multiply is a little slower than add, not a lot slower, and it does a whole bunch more work. That's the deal. Okay, and it has this drawback that it's hard to write in C. Comment, we're going to have parallel computers. We're stuck. We seem to have finally hit the end on Moore's law. If you look at what the clock speeds are and the chips coming out, they're no longer getting faster clocks. They're giving you more cores instead. The transistors are still getting smaller, but they're not wiggling as any faster. That's the pitch. Comment on simplicity. Everyone likes simplicity. It's pretty, it's beautiful, it's risky. And I'm going to skip on the questions because I want to get to part 2. And now for something completely different.
Can I interrupt with a question?
Yes.
We're going to something completely different. Using multiplication as a core mixer, it's a great mixer on devices that have a nice 32 by 32 multiplier.
Right.
This issue came up in the AES competition.
Yeah.
And the problem is, it's really a bear when you try to have implementations on small devices.
Yeah. So if you don't have a multiply instruction at all, you've got to find some way to do it.
Or even just, if you've got an 8-bit multiply, it's going to...
If you've got an 8-bit multiply, then you'll be doing 4 by 4, 16 of them, and on the adds and carries and so on. The plus side of that, we've only got 5 rounds in the compression function. The total number of multiplies to do a compress is going to be, let's see, about 3 times 30. I think the aggregate is going to be under 200 multiply instructions. And that's actually comparable to the arithmetic you're doing anyway. So there's probably a penalty, but it's not a kicker terrible penalty. We have less of the other mixing is what it comes down to, because the multiply substitutes for a lot of that. You can't just have pure arithmetic, though, or you'll get killed in a different way. Okay, and now for something completely different. Those of you who have never heard of elliptic curves can leave. Okay, this is a talk about scalar multiplication of points on elliptic curves. P is usually a point on an elliptic curve. K is usually an integer, and we want to compute K times P, another elliptic curve point. Mostly we're working on the Galois field GF2 to the n, mostly. Mostly we'll use affine coordinates, which means just x and y. And our elliptic curve equation is usually this standard one. In fact, usually A is either 1 or 0. Yeah.
On a GF2 to the n, don't you have a different formula for the elliptic curve? Because
squaring
is a linear operator. And
yes, it is. This is that different formula. In the mod P systems, well, everything except mod 2 and 3, you would instead have AX here instead of AX squared.
There's an XY term.
Yeah, right. Oh, I left out the XY. Ooh, bug. No, I can't edit it. Okay, there should be an XY term here, as Peter points out. God, I've shown this slide I don't know how many times and didn't catch that. And nobody in the audience caught it either. Okay, the usual way of computing a scalar multiple is called double and add. But when you look at it closely, it turns out there are 2 ways to do double and add. There's top down, left to right, and bottom up, right to left. And this is I lost it. Pardon me, I have the wrong talk. Oh, no, it's here. Okay, sorry. Okay, the key idea. We use the bottom-up scheme, and we postpone adding up the points. So the bottom-up scheme calculates P, and then 2P, and 4P, and 8P, and so on. And it saves the ones it needs, which is usually about half of them. And then we do all the adds at the end. The point of doing that is that you can share all the reciprocals, using Peter's trick for sharing reciprocals. And this actually works quite well when the cost of a reciprocal is more than 3 times the cost of a multiply. Okay, here's the double and add slide again. This is a photograph and I got the lighting bad, but it illustrates how you process the bits in the multiplier. You can either go left to right, this is top down, or bottom up, right to left. And the scheme I'm suggesting here uses bottom up, right to left. And they went ahead and did a patent application without asking me, although I had to provide input. But then it was dropped, so it's unpatented at the moment. This is the regular double and add scheme. You have a doubler here, and when appropriate with the control, you add into the running sum. This is the same thing, except the add step has been revised. You save the multiples you want. You use Peter's reciprocal sharing trick. You pair all the points. And each of these octagons is going to compute a reciprocal. And you arrange to have all these reciprocals be shared using Peter's trick. And then you have your point additions. You now have half as many points. And you do it again, and you do it a few more times, and you're done. So the total number of reciprocals you need to add these affine values is like 6. That's the deal. All the others are replaced by 3 multiplies instead. And these are the formulas for a conventional point addition. You get the slope of the denominator is the sum of the 2x coordinates. You do a reciprocal. You multiply to get the slope of the numerator. M is the final slope joining the 2 points. The x formula is just this. The y formula is this. That's what happens in the regular way of doing an affine addition in GF2. The rearrangement you make for my scheme, you compute the denominator as standard. You then have all these octagons that are sharing the reciprocal operation, and then you do the rest of the processing as Stanford. I prefer the word reciprocal to inverse because reciprocal is much more specific than inverse. Okay, this is Peter's trick. It's actually probably Peter's 17th trick because Peter has done a number of tricks. It sort of could be called one more reciprocal, in that if you've already got one, you can get another one, sort of. And I was talking to Peter. We're not sure if he originated it or not. It's certainly independent with him, but it's possible it was something that was known to people in the 50s, from way before I started using computers. It's a sort of trick that would be in the lore, but never get published. Suppose I need 2 reciprocals of A and B. I do the following thing. I compute A times B. I take that reciprocal, and then I can separately multiply that by A and by B to get the 2 I need. Now, in what I paid here to do this is I've got a multiply here, here, and here. So I've paid three multiplies, and I've gotten rid of 1 reciprocal. And there's a very easy way of extending this so that you can do k reciprocals, bring them down to 1, and the k minus 1 things that you replaced become 3k minus 3 multiplies.
So in your chart before, when you had, let's say there were it was an n-bit number, k was an n-bit number, and so you have like n over 2 octagons at the first step.
Right.
So your little k here is n over 2, so 3 times n over 2 minus 3, whatever, 3
Right.
minus 6
Yeah.
or something like that.
Right.
Then how come you said you pay only 3 multiplies each of those steps? You pay like 3n multiplies at that stage, and then...
Each octagon costs you 3 multiplies. So the work per bit is 3
you don't put
multiplies.
them all together then? You don't do like k reciprocals all at the same time?
Well, you're making that you're getting that result, but you're getting, let's see, let's suppose you're adding n things, which is you probably had a 2n bit number, but you're adding n things you've got to add up. So you pair them, you have n over 2 pairs. So the first layer of octagons, you have n over 2 octagons.
Yeah, but so you want to do it 2 by 2. You don't want to do all of the. You don't want to share 1 reciprocal for all of them.
No, you share 1 reciprocal for all of them.
Oh, okay.
So you pre-compute each sum of x coordinates, each pair. So that's going to be, let's see, if you have n over 2 octagons, you're going to be doing n over 2 additions at that point. You need n over 2 reciprocals. That's going to cost you 3 times n over 2 minus 3 multiplies.
Right.
One reciprocal. So the number of multiplies that it costs you in each octagon is just a little bit less than 3.
Oh, I see, per octagon.
So each octagon achieves one addition. So the total number of additions you need with all the levels of the tree is going to be one less than the total number of things you added. Okay, now whether this is worthwhile depends on the cost of a reciprocal versus a multiply. This can be quite low if you're using field towers, but we have on good advice that we shouldn't use field towers anymore. The typical reported value for this ratio is 10. My personal experience is actually a much smaller number, but still bigger than 3. And if you're doing it mod p, the scheme works mod p, it'll operate. The typical cost of the reciprocal is 60.
So, 2 questions. First line, why do you say SUN IPC for field tower?
That's where I wrote code to do field tower. I was comparing 155 using conventional and 156 using a 3-level tower. And that led, for that particular machine, this is, 1997 or something, I got a ratio of 1.5. And the reason it's so low is that the actual number of reciprocals you do is 1 in the base field. And my base field was GF2 to the 13th, and I just did a table lookup for that final step. And actually, that was sort of cute. I had a bunch of logarithm tables and exponential tables for doing GF2 to the 13 arithmetic. It's like 4 instructions.
And then the other question is, so for mod p, this depends a lot on the prime, the size of the prime, the
Absolutely,
picture, all of that. So for many years, Peter had a ratio of about 5.
Oh, okay, all right.
And then with special instructions to speed up the multiply, it's up to 10 now.
Mm-hmm.
But that's on cryptographic sizes. So we've always maintained this 60. What you see in the literature, sometimes you see 80 too.
Yeah.
This is very close when you're using special primes, like percent primes.
Yeah, right.
So where's your 60 coming from? Is that special
That's just pulled
primes?
out of the literature.
Yeah, okay. So that's more typical if you have a very special prime.
Yeah, okay. I'm not going to quarrel. I'm just saying the numbers are obviously highly variable, and whether this scheme actually buys you anything will depend on your circumstances. I should mention we had some students code up the mod p one. They were looking for a high school science fair project, and they found that the overall scheme gave only a slight improvement, like 5 or 10% over a projective implementation. Now, I thought they could have put more work into speeding up the reciprocal, but it was time to turn in the project, and they'd already written a lot of code. So anyway, I think in the mod p case, they would actually perform also. There's a complication in mod p. I hope we'll get to it. Okay, this is the summary of elliptic curve addition for GF2 to the n. It's very similar for mod p, but you have to count the squarings in mod p. In mod 2, you can pretty much ignore the squarings, so they're a minor cost. Okay, this is just a repeat. Okay, in general, for point doubling, if you're doubling points in projective, you can do this interesting thing. You can do a series of doubles in projective form, mod p. And then, one of the benefits you get just incidentally in passing is typically the z-coordinate from one point is a divisor of the z-coordinate for the next point. And that allows you to slightly simplify Peter's trick. You save one multiply because of that. Anyway, you collect all the points that you need to add in projective form, and then you can convert them all to affine at a cost of only 1 reciprocal. And I think it's 2 multiplies per point that actually needs to be added. And then the net result on that, it may be a benefit. It depends on the cost of your reciprocal or not. However, if you can do point halving, then you don't need reciprocals you don't need a doubling chain. You can have a halving chain, and there are no reciprocals to compute at all for that part. So the combination of point halving together with the reciprocal sharing trick to do the addition tree is the most efficient way of doing GF2 to the n. It's even better if you have Koblitz curves, because then even your point halving gets simplified. You can replace that with a doubling substitute, which is multiplying by this gadget. And some of you must know what this is already, and the other people, I don't want to take time to explain it. So it's basically you can use that as a multiplier. And your main cost at that point is the additions. And this new way of doing the additions is a nice help on that. You can even cause yourself to have fewer additions if you pre-compute a bunch of multiples. So for example, tau plus 1 and tau minus 1 can be used as, when you group together, you do your base conversion to base tau, and then you group some of the bits together, some of the coefficients, and you can use tau minus 1 and tau plus 1. The doubles and halves of these, well, the tau powers of these are just rotations, so you can compute them on the fly. And that's what makes it nice to have several available digits in your representation. Okay, these are just various circumstances that win and don't win. There are a bunch of different things you can do. You can double in groups. If you don't want to build the reciprocal circuit for some reason, you can take a penalty and compute it this way. That's old news. And we did an implementation with a generic affine curve and got a 30% speed up over the simple projective. And if you don't have the memory to store the points, if you can store a few points, you can get a large part of the benefit. So this is going back to your smart card situation where you have room to store 4 points or something.
So when you say 30% over the projective,
Yeah.
what can you be more detailed about that comparison? So projective using the same double and add strategy, like the same windowing and all of that, or?
I don't remember. I didn't do the implementation.
Because it seems like it would be good to compare it to just the regular affine without your trick.
Oh, it'll kill affine.
Yeah, obviously.
No, but you'd want to compare it to the best other choice, which is going to be probably some variation on projective.
Yeah, but I would say that comparison is going to have to vary widely.
Absolutely. Yeah. So what I think this comes down to is it's one more variable in the use this, this, and this, but not this, this, and this when you're actually making your engineering choice. I guess from my personal viewpoint, I like to be at the fast high end, but that's probably unrealistic in terms of when people are actually building a system. But it does provide another option in building the thing. Does speed ever actually matter? Occasionally it does. Most of the time, well, no, actually, it doesn't. You need it to be fast enough, but not fast as possible. Okay, well, also, this is just other things you can do with it. One interesting addition, because all the doublings happen before all the additions, if somebody's listening to the ka-chunka noises, they won't get the information that they would usually get, where you have one kind of ka-chunk for the multiply and a different kind of ka-chunk for the double and so on. Okay, and we have a few minutes for part 3. Where's part 3? Yeah. Okay, this is fun and games. And I don't have time to do everything here, so I'll pick a couple. I did this and I gave a talk about it and sent it off to people. And then I got this letter back from Don Zagier saying somebody named Dennis had done something very similar many years ago, although it was not published and nobody knew about it. Okay, there's a function called the Dye Logarithm. It's an analytic function. It's way back in the special functions section of the Big Blue Book. It's basically what you want to study if you're trying to evaluate zeta of 2. So Euler was interested in it. It also shows up if you've just invented integration and you're running around trying to figure out what is the integral of tangent and so on. One of your very beginning steps is going to be to differentiate a bunch of things and see what the results look like and then try to work backwards. And then you're going to come across a bunch of things that seem like they ought to be simple enough to integrate, but you can't quite do it, like the error function. Another one is this very simple log expression here. And you can write the power series for that easily, and you can integrate the power series as long as you're in the unit circle and so on. And you wind up discovering this special function. And beyond that, you don't think you have much need for it. The following functional equations are in a sense trivial. They either appear directly from the power series or it's what happens when you try integrating or differentiating combinations. You can check these trivially, and you probably don't remember from high school, but when you tried to integrate sine times cosine, you got back cosine times sine or something. And then you could just do this little tricky manipulation, and all of a sudden you had your integral. And people were doing similar things with that integral I showed you earlier. So you discover these functional equations easily. Then if you're really brilliant, 100 years later, you find this. This isn't what Spence actually found. He found something that's equivalent to this, because I don't think he was actually working with Li2, but 1 minus it or something. This is really weird. This first part of it is actually like the regular functional equation for logarithm. But then there are these extra terms. This extra term explains my interest. What I've done here is I've converted this function into a modular function. If there were magically some way to compute these guys, modular, I could do this one. This one I have a lot of interest in, because it would also be modular. Let's see, I worked with what I call the cos dialog, which is this very similar thing, but it has an easier functional equation. So, it's one you can remember and write down and work with. This one you need to have sitting in front of you all the time to do anything with it. This one is actually true for regular logarithms, interestingly enough. Yeah?
The last term of the top formula is not symmetric in x and y, is it?
Well, it's squared. So if you swap x and y, the logarithm's negative.
Oh, the logarithm is squared. Okay, sorry.
Yeah. Okay, here's what's going on. My question was, is there a modular version of the dialog that satisfies the same identities? Now, there's an analogy with discrete logs. If you look at, they're actually a whole collection of functional equations for this thing, and they have lots and lots of log terms in them. So you could imagine that part might work. The drawback is there aren't very many rational values to work with. If you're trying to extend ordinary logs or exponentials from integers or rationals over to mod p, you have a bunch of rational values you can match on. You can say, I'm going to say log 2 is this one value, and then I've automatically got log 4, log 8, and so on. It's not so easy with dilog. There's some question as to what would this even mean. The domain presumably is going to be modulo some prime. The range, well, we're not real sure about the range. It's probably got a p minus 1 in it because we had those log terms. And logarithms mod p come out mod p minus 1. Another problem with dilog is that there are Riemann sheets, and there are infinite values at a few places and things like that. And I simply ignored that problem. You know, if I had an equation that involved a 0 or an infinity in a bad place, I'd just say, all right, I'll let that one go. Here's what we're aiming for. And the answer is, okay, logarithm, a plain old log, is 30103. We remember those. We can do a discrete log in which the log part is mod 19, and the answer comes out mod 18. Now for Dye log, the Dye log of 1/2 is 0.58 mumble, and there's actually an expression for this involving pi squared and the square of log 2 or something. And the modular Dye log of 1/2, mod 19, is the same as the modular Dye log of 10, and that turns out to be 265, interpreted modulo 360. 360, of course, is 1 less than the square of 19. So this is the table, the Dye log table for mod 19. If the residue n is one of 19 values, then the Dye log is one of these. And I wrote a program, of course, and I have solutions modulo p, as for primes ranging from 5 up to 23. The answers always turned out to be modulo p squared minus 1. Now my code was actually agnostic on the modulus. It allowed for the possibility that the modulus might have come out to be anything. And that involved keeping a couple of extra degrees of freedom in the intermediate stuff. And it always turned out to be p squared minus 1. And I asked what happens on non-prime moduli, and the answer, you can get this same table, mod 25, and the answers come out mod 600. And then I said, what about GF 5 squared? And then the answers come out mod 624, which of course is 5 to the 4th minus 1. These are the functional equations satisfied by the discrete Dye log. And I should have put the real complex valued ones up here to match, but they basically match. The one minor gimmick is there's a constant involved, and that depends on your choice of base for the Dye log and your choice of base for the log. But it satisfies all the Dye log functional equations. It turns out, magically, that every time a log of 0 appears in one of these, like here, it's always multiplied by the log of 1. So you just say by fiat that log 0 times log 1 is 0, just like you do in information theory. And everything plays. It turns out you can do trilogarithms. That's the same power series, only you have cubes in the denominators. And that's what you study if you're interested in zeta of 3. There are many functional equations. I was only able to get one of them to work. I tried 2 or 3. It has 20 odd terms in it. It's a mess. The solutions come out to be either mod p cubed minus 1 or 7 times that. And I suspect if I introduced an additional functional equation, the 7 option would disappear, and it would just be p cubed minus 1. But I never checked it. Whether you can do higher polylogs, I don't know. Maybe. Okay, now, does this represent anything real? Is there something at the bottom here? This is stuff that I learned from other people. It was the letters Zagir sent to me mentioned this stuff. There's a puzzle on why does this exist. Every simpler function, add, subtract, multiply, exponential log, trigs, elliptic functions, and so on, can be brought down to a base that reaches either the integers or the rationals. And then you can just move forward modulo p in that basis. And if you want to move over to a finite field, you actually use algebraic numbers as some of your ingredients. This does not touch down, this has no base in that sense. A particular value is neither right nor wrong. It's only a collection of them that allows you to decide if the functional equations are satisfied or not. But you can't just say an individual Dye log value is so and so. It only makes sense in the group context. It'd be interesting to have a better way of calculating them. If you had a really good way, then you could use it for discrete logs. The ways I have are not really good. And I'm sort of wondering, to what extent can this be extended? I know I can extend, I have similar examples with theta functions, which have the similar property of no rational basis, being free-floating. But I was able to come up with I think it's mod 41 or mod 43 with the theta 0, 1, 2, 3, 4 stuff that satisfies all the functional equations. So what I'm thinking is a large part of our special functions have mod p analogs, and it'd be worth and interesting to investigate them. Okay, and I should let you go. Anyone who wants to hang around, we can talk about the other stuff or answer questions or anything, but I've gabbled on for an hour.
Could you send me your data on memory uses and I'll update that in?
Of course.
SANDstorm.
Sure, yeah. I'll find your address, no problem.
Niels at Microsoft. How's it going?
The Niels? Wow, okay.
More questions?
How much information does a multiply leak via power analysis and timing analysis? But one thing engineers always optimize.
Yeah. A typical processor today, if you reach into a barrel and pull out a processor, the multiply time is independent of the operands. There are a number of exceptions.
No early out?
I've been trying.
No, that's the length.
Yeah.
I'm saying?
I've been trying to get Intel to promise us no early outs, but it is true today. But
They're not doing early out? Wow. Okay. Fine.
So little of the the arithmetic is such a tiny part of the total.
Okay.
And to screw up your timing chain just because the data changed, you've got all this.
Used to be everybody did it.
It used to be, but you can't change the timing on a cycle now. You don't want to, because there's this march going on of data coming in and going out into the cache, and every time you introduce an uncertainty into that, you've got to pay 10 engineers to figure out what it means.
Okay.
Now there certainly are machines that check for 0,
Yeah.
and things that it depends on how many 1-0 transitions you have and things. I worked on those machines a long time ago, but. Let's see, what was your other?
There's power.
Yeah, there's power. I don't know on that. Very possibly it's a problem. But on the other hand, if you can look in the hash function, a lot of them, it depends on the power. These guys have adds. How many carries?
If you do any gate transition, the power depends on what the data you're processing.
Okay.
There's no defense against that stuff.
I mean, the two sides of XOR, whether it was X is 1 and Y is 0, or X is 0 and Y is 1, they might have different powers. The answers might arrive a picosecond before the other. It's, yeah. No, anyone else? Thank you.